Let's continue our discussion on dimensionality reduction. And this section we are focusing on discussion of kernel PCA and LLE. Kernel PCA. In the SVM study, when we studied SVM classification and regression, we introduced something called kernel trick. Kernel trick is a mathematical technique that implicitly maps instances into a very high dimensional space called the feature space so that you are able to run nonlinear classifications and regression easier. So for example, a linear decision boundary in a higher dimensional space corresponds to a complex nonlinear decision boundary in the original space. So you would be able to leverage that linear decision boundary in higher dimensional space better. So in the scikit-learn, you could leverage kernel PCA by doing this. Just define the number of components and then define your kernel and the corresponding parameters of gamma. In this case, we use something called IBF, radial basis function kernel in the kernel PCA. These are just a couple of examples by doing different kernels, linear kernel versus IBF kernel versus sigmoid kernel. Just show you for the Swiss row dataset, if you original three-dimensional Swiss row dataset, if you do a kernel PCA using different kernels, what the output would look like. The question is really which would be the best kernel that you should be using in your kernel PCA. Now, in order to select a kernel, you should leverage this by a two-step pipeline. First of all, you do reducing dimensionality using kpca, and then you run a largest regression for classification. And you use grid search to find the best kernel and gamma values for kpca. So in this pipeline, you can see that you do kernel PCA, and then you do logistic regression, more or less, right? Your PCA is still a dimensionality reduction approach, so that you are able to once you have the reduced dimension data, you are able to leverage a logistic regression to do the classification. So in this case, in this pipeline, you have two components, kernel PCA and logistic regression, and you want to search different kpca gamma, and then you have different kernels that you want to experiment on. You use grid search cross-validation algorithm to go through this CLF and parameter grid with cross-validation equal to 3. And then you can fit that x to y. At the end, you want to grid search best parameters. Turns out to be, in this case, would be gamma being 0.04 and kernel being IBF, which essentially says that the middle one is a better representation, just simply because you're able to differentiate those yellow points versus the red or some dark points much easier comparing to the other two graphs. Okay. And you could also leverage something called by doing this reconstruction, the whole reconstruction process, whichever one the kernel actually is able to yield the lowest reconstruction error, then we would see that that would be the kernel that you want to pick. For example, you start from here, original space, you run the kpcalle so that you come to the second two-dimensional space of reduced space with all those points. And then you define the feature space based on those directions of that PCA, and then you run through the reconstruction process to come back with a reconstruction of the image, and then check the error between the pre-image original space and the reconstruction of the image to construct that reconstruction error so that you want to find the corresponding process that would yield the lowest reconstruction error. That's kernel PCA. Now we want to move on to another methodology called locally linear embedding, LLE in short. It is a manifold learning technique that does not rely on projections like the previous algorithms do. So PCA is based on projection, kernel PCA is based on projection, but LLE is based on manifold learning. In a nutshell, LLE works by first measuring how each training instance linearly relates to its closest neighbors, and then looking for low dimensional representation of the training set where these local relationships are best preserved. So you have each point or instance, you have a bunch of neighbors of this instance. In the LLE methodology, you're trying to preserve that local relationship, that closest neighbor relationship with this point should be preserved as much as possible. So that's high-level discussion of locally linear embedding. And in scikit-learn, you can leverage by doing locally linear embedding class, and then number of components equal to 2 and number of neighbors equal to 10, so that you would be able to come back with this reduced X. This is really a high-level discussion. There are more detailed discussion of the algorithm itself. You could read through and try to understand LLE. And then beyond this, okay, we discussed PCA, kernel PCA, LLE, and there are many other different dimensionality reduction techniques. Hopefully, down the road, you would be able to have exposure to all of this, some of this at least. And but at this level, just pay attention which would be the key ones. It would include random projection, multi-dimensional scaling, isomap, t-distributed stochastic neighboring embedding, T-SNE, and the linear discriminant analysis. And as a result, you can take a look at this example on the right-hand side. You use different techniques to reduce the Swiss roll dataset to 2-dimension. So MDS output look like this, and isomap look like that, and the TSE look like this. Conceptually, if you look at those three, you probably think that isomap and TSE might doing a better job than MDS, right? Of course, it really also depends, right? It depends. If you use support vector machines on top of the MDS dimensionality reduction, you probably still can do a decent job. In general, all of those three are doing a decent job, by segregating the different colors or different features, different observations into a lower dimensional space, two-dimensional in this case, Z1 and Z2. These are the key directions that you might want to look into in the future in case you want to leverage some of other dimensionality reduction techniques. This would be everything. That concludes our discussion on dimensionality reduction. Thank you.